All right, welcome. Today, we are diving deep into abstract algebra. We're going to uncover this really powerful tool that mathematicians use to see the secret connections between different systems. Systems that, on the surface, look like they have absolutely nothing in common.
So here's the big question, right? How can you have two things that seem totally different? I don't know, say one is about adding numbers and another is about rotating a triangle. How could they possibly be the same underneath it all? Well, that's the puzzle that leads us straight to this idea of a homomorphism. To figure this out, mathematicians came up with a really precise tool. And the key to the whole thing, believe it or not, is usually buried inside a pretty dense-looking textbook definition.
Okay, yep, at first glance, this page looks like a wall of text. You see all the symbols, the formal language, it's a lot. But don't worry about it. We're going to pull this apart piece by piece, and I promise you're going to see this really elegant, simple idea hiding right there.
So, the big idea is this. We need a special kind of function, which we call a map, that can act as a bridge between two different mathematical groups. But it can't just be any old bridge. It has to be one that respects and preserves the structure, the very essence of the groups it's connecting.
And that brings us to the main event, the most fundamental kind of structure-preserving map. The one that really gets the whole thing started is called a homomorphism.
So here's the formal definition, straight from our source material. We've got a map, we'll call it F, and it connects two groups, G and, say, G prime. But for it to earn the title of homomorphism, it can't just be a random connection. It has to obey one single, incredibly powerful rule. This is it. This little equation right here is the heart and soul of the entire concept. Seriously, everything we're about to talk about boils down to this one beautiful, simple statement. And that's the key, This isn't just a random jumble of symbols. This formula is the secret sauce. It's the guarantee that the relationships between the elements are the same on both sides of the map. It ensures the very fabric of how the group works gets carried over perfectly. Let's really break down what this is saying. On the left side of the equation, you take your two elements, A and B, and you combine them first in their home group. Then, you use your map F to send that result over to the new group, okay? Now, on the right side, you do it in the opposite order. You take A and B and you map them over separately first, and then you combine them using the rules of the new group. A homomorphism is a map where it doesn't matter which path you take. You always land in the exact same spot.
Okay, so now that we have that basic rule down, our textbook starts to make a subtle but really important distinction. See, not all of these maps behave in exactly the same way.
Right, so a standard homomorphism is called into. Think of it like this. It takes elements from group G and lands them somewhere inside G prime. Maybe they all cluster in one little corner, but a homomorphism onto is way more powerful. It guarantees that the mapped elements from G completely cover all of G prime. Every single element in that target group gets hit by something from the first group. And when that happens, we call G prime the homomorphic image of G.
Now, this is where it gets really interesting. What happens when we add just one more condition to our structure-preserving map? We go from just comparing two groups to proving that they are, for all practical purposes, the exact same thing. Our source calls this perfect match an isomorphism. So, to be an isomorphism, a map has to be a homomorphism, and it has to be onto, meaning it covers the whole target group. But it has one extra critical requirement. It also has to be one-to-one. So what does 1-1 mean? Well, it's pretty much exactly what it sounds like. Every single element from the starting group G maps to its own unique personal destination in G prime. No two elements from G are allowed to land on the same spot. It's a perfect pairing, one-to-one. And this slide just lays out the difference perfectly. A homomorphism shows that two groups kind of have a similar structural vibe. But an isomorphism, that is a huge statement. Because it's 1-1 and onto, it proves that the two groups are structurally identical. They are literally just different versions, different labels for the exact same underlying idea. Okay, there's one last variation our textbook gives us, and it's a pretty fascinating special case. What happens when a group isn't mapped to a different group, but instead gets mapped back onto itself?
And the name for this is an endomorphism. Just like the slide says, it's a homomorphism from a group back into itself. The map starts and ends at home.
A good way to picture this is taking all the elements of a group, shuffling them around based on a structure-preserving rule, but then placing them all back down inside the very same group. It's a way for mathematicians to explore the internal symmetries and the deep structure of a single group.
So let's do a quick recap of our little family of maps. The homomorphism is our base model. It preserves structure. If it covers the entire target group, it's a homomorphism onto. If it's also a perfect one-to-one match, it gets upgraded to an isomorphism. That's the gold standard, showing two groups are identical. And if a map just goes from a group back to itself, we call it an endomorphism.
And that leaves us with a really big, kind of philosophical thought to chew on. If an isomorphism proves two groups are algebraically identical, they follow the exact same rules, just with different names for the pieces, are they really two different things at all? Or has math just given us a way to see one single, beautiful idea wearing two different costumes? Something to think about. Thanks for tuning in.